Hi everyone, welcome to this presentation on all things ML. I'm Jakob Ringler, I'm a TD at Side Effects, and I'm going to be talking about cells, pixels, points, and splats. And I will cover 3 topics today that are new to Houdini 22. The first one being Neural Cellular Automata, or NCA, about which I already presented in this very location last October. So there's lots of new stuff, so if you've been there, bear with me. After that, I will look at more neural nodes that made their way into COPS before diving into Gaussian Splatting in Houdini. Before diving into those neural cellular automata, we will look a bit back in time. The core idea of what I will show today is cellular automata. And one, if not the most famous of those cellular automata, is Conway's Game of Life. Most people have probably come across this at some point, and the way Game of Life works is very simple. Each cell in a grid runs its own little code snippet that decides what to do based on its neighbors. In practice, there are 4 very simple rules that control whether a cell dies, stays alive, or becomes alive. Those very simple rules already lead to very interesting emergent behavior that isn't programmed in any way. Depending on how you initialize this grid, you can get very different outputs. Another one of those cellular automata is reaction diffusion, which is also part of Houdini since 21. Reaction diffusion works in a very similar way, but it tries to emulate how 2 chemicals mix. There's also a single algorithm that runs on each cell, but instead of the 4 rules we had before, it uses a bit more complicated formulas that try to emulate how those chemicals react with each other. But just like before, a single cell can only see its direct neighbors, and those patterns emerge by applying the formulas to the data in each time step on each cell over and over again. Now that we know what the general idea behind classical cellular automata is, we can look at what the neural prefix is supposed to stand for. Instead of running a small algorithm on each of those cells, we can run a very small neural network. And instead of programming the rules ourselves, we can train a network to come up with the rules that fit our target use case. The network should ideally learn how to produce a bigger given pattern based on looking at it. This happens all the time in nature. Look at zebra stripes, for example. Each cell in the skin of a zebra seemingly knows whether it's a black or a white cell and what kind of hair to grow to create this infamous zebra stripe pattern. But no cell can ever see this entire zebra at once. At the same time, not every zebra is the same. There are no pixel-perfect copies of different zebras. And patterns like this are often the result of very simple rules that drive local processes. And to train a network to generate a pattern, we need some way to determine if the output of the network is close in terms of style to our target image. We don't want to measure pixel differences here. It's more about seeing if the general shapes and the colors match to our target. The idea comes from this self-organizing textures paper from 2021. They applied a technique discovered for neural style transfer where you're using a second pre-trained neural network's activation functions to determine whether the image contents are similar in terms of style. If you're interested in the specifics, I recommend checking out the distill blog shown on the right here. It has a very, very accessible explanation and even comes with this live demo to play around with. But if you want to learn how to do a basic implementation of this in Houdini, you can watch the older presentation I did last year on the topic. But for anyone who just wants to use it, the good news is that you will be able to do so right from within COPS in Houdini 22. Before we dive into any examples, we need to look at what kind of network we are dealing with here. Fundamentally, the network is a convolutional neural network. It uses hard-coded convolution kernels to see its neighbors. You use convolutions all the time in compositing or image processing for sharpening, blurring, and other operations. But those specific kernels give the network the local image gradients, so basically the rate of change across pixels. This is the perception part of the network and models how the cells see their neighborhood and surrounding. Here you can see the entire network, and the kernels are this iKlab, ky, kx box in the middle. After those perception kernels follows a super simple neural network, and the network outputs multiple channels, which includes RGB and a few extra channels. And the predicted result is then added to the input to iteratively update the result in each time step. The other information in these extra channels I mentioned at the previous slide. Oh, no. Yeah, okay. I mentioned the previous slide. store latent information that the model comes up with itself, sort of like a local coordinate system. Those resemble something like normal map or position passes, but it's not really position data. It's more like a local fall-off or geometric gradients that describe the pattern's relationships. It helps the cells orient themselves within the pattern, know what they should do in the next update. This is more or less the state of the prototype I presented last time I was here. But it has like one big major flaw. Performance scales quadratically, and running even a small 10K parameter model on every single pixel only goes so far. Also, running it once may be fine, but multiple times in a loop at resolutions of over 512 by 512 lets you really feel the hit on performance and your VRAM. Since then, there was some research being done that proposed a split architecture. The idea is to split the task of rendering the fine details in the texture from the evolution of the cell state. So cells can still operate at a lower resolution, but a second model is used to decode or effectively render those latent cell states into the correct RGB image. This makes it much more useful for typical working resolutions, and that's exactly how we implemented it for COPS. You can get an NCA core node that will do the NCA inference logic and outputs the cell state into an NCA decode node that takes care of the rendering and upresing. Now you may ask, okay, how do I get my own NCA into COPS now? First, you need some kind of pattern-based target image. For example, a close-up of your genes. You crop it and pre-process it a bit and turn it into a reasonable target square. In COPS, you find the ML train NCA recipe. All you need to do is plug in your target image. It then shows you a little helper layout that helps you check for some of the most common pitfalls. The most important one is scale. The general pattern should ideally still be visible at a low-res NCA resolution of 128 by 128 during training. This also relates to long-range dependencies. Generally, a single feature in the pattern shouldn't be bigger than, say, 10 to 15 pixels in the low-res state. The more cells an element covers, the harder it becomes for the NCA to update and propagate this information across the entire image. The update range is only a single pixel per iteration, after all. It also should have as little noise as possible, and it should be actually pattern-based, so those crops you see on the right here should show similar content. And generally, you want to avoid fine details that turn into sub-pixel detail on the NCA grid. Then all you need to do is click the cook output button, which kicks off the training process that runs in TOPS. You can watch the training process in the ML training monitor. There's a view for the total loss as well as the individual loss components that make up that total loss. And besides the loss, you can also check test outputs that are produced during training. It lets you see how the model progresses over time. As you can see here, we go from gibberish to a pretty accurate denim texture in a few steps. The chart on the right visualizes at which upresing scale and detail level the loss is the highest. So now that we got all the technicality out of the way, we can look at some examples. Once trained, when the training concludes, you can drop down the Neural Cellular Automata recipe and load your model into COPS. You can set how many iterations you want to run the model on the core node, and if you don't like the content, you can simply change the seed and generate a new variation of the same pattern. You can also define the desired upres resolution of up to 8x on the decoder node. This can be very handy to, for example, create a very fast proxy output and a final high-res one, and you can switch depending on what you're working on at the moment. At the end, I'm also visualizing those different cell states that drive this under the hood that you can also look at and maybe use to further refine your output. Here's the target and the result side by side. Can you guess which is which? It's pretty close, right? It's also not limited to square textures. While you train on a 1024 by 1024 target, you can inference on practically any resolution your VRAM allows. It also stays tileable at non-square resolutions. The way this is set up means that pixels at the border wrap around and see the other side as their neighbor. So out of the box, everything is always tileable. Of course, it doesn't have to be run in a single cook and produce a static image. You can just as well make use of the NCA block recipe, which you can find in COPS. It simulates this over time, opening the door for all sorts of effects and motion design setups. Here are two other ones that were trained on images of different roof tiling. you can see the cell states on the right here and how each NCA learns its own latent space that is entirely different from each other. Here are a bunch more NCAs I trained to test how well certain patterns work. For simplicity and comparability, all of those are running in black and white, but it would work for any kind of coloration, really. And another set, you can really see where it struggles with the long-range consistency at the top right here. It can't get those horizontal lines straight. To look at some ways how we can control that simulation, let's just use a very simple regular stripe pattern for now. By default, the cell updates happens randomly on a subset of cells on each iteration. Using mask, we can drive the strength or the probability of the update per cell. So you can use a simple ramp or any more complicated monolayer to drive the growth. As I explained before, each cell sees its neighbors using those hard-coded convolution kernels. What you can do purely at inference time without changing how you train is rotating those convolution kernels. And through that rotation, the perception of the cell leads them to produce those rotated patterns because they believe they are still creating a straight line, but really the world around them has warped. You can drive it with a simple ramp or any more complex input layer you want. Another inference time trick is to scale this local perception gradient. You can do this for each axis individually and through that influence how far a cell can see and therefore produce smaller scale patterns. That only works for values less than 1, otherwise it becomes unstable, but you can already do a lot with that. Of course, you can apply any other COPS tool anywhere in the loop as well. For example, distort the cells and create those liquid honeycombs. After each time step, the cell update fixes any damage that was done by distorting and keeping the pattern alive. To drive that point home, I turn off the NCA update halfway through the solve here, and everything becomes very blurry, and any shapes quickly dissolve over a few frames. But enabling it again brings back all of those details. The NCA keeps all the shapes intact by constantly fighting against the blurring and caused by the distortion, but it doesn't really care about the moved cells because locally each new pattern is still a valid resolution or a valid result. It doesn't just have to be slight distortion, but it regenerates complete damage. And I'm sure this can be used for some interesting organic growth or regrowth effects. So now you may think, yeah, kind of cool ML image processing stuff. But this is a 3D software after all, right? Why can't I run this on meshes and make a zebra capybara, for example? And while you can't run on meshes directly, Houdini 22 introduces a concept called Adjacency rasterization we already heard about today. It lets you compute all the information needed to allow solvers and other COP nodes to jump seamlessly between UV islands. And that also works for NCAs. If we use this logic combined with the scaling and the rotation functionality shown before, we can get seamless inference on any mesh with proper UVs. You can combine this with all of the other control inputs available. Here I'm creating a mask from the position pass and a position-based noise to drive the rotation and scale. And this already lets you create quite intricate effects. And remember, this is still just simple stripe pattern. Without any other changes, you can swap out the model and see the same effect with different NCAs, for example, swirly denim, honeycomb, or green-tiled capybaras. I'm not sure whether you should, but certainly no one is stopping you. What we can also do is to blend between two patterns, and I'm not talking about blending the final result of two independent ones, but to blend the cells of two models in the block. Since the cell states are custom in each NCA, we need to train a bit more carefully to produce a state that can be blended between. This can be done by alternating the target texture during training. And after every few hundred steps, we switch from target texture A to target texture B, which leads to the model converging to a shared local latent space. To do this, you can make use of this partial training mode on the top node and run it in a for loop. Each loop iteration, we run the example for 500 steps and set the target texture to one or the other image. And in the next iteration, the training resumes with everything it has already learned from the first texture, but a new target texture. And we do this for a good amount of steps before fine-tuning on one or the other image. And this is how the output looks. And as you can see, the cell states in the middle share a very similar value range. So all the colors match left and right. And they use this to encode different features. This makes it incredibly easy to blend between them meaningfully. And to blend, I just use a simple mask that drives the update on each of the NCA core nodes. And one gets the normal mask, the other gets the inverted one, and they operate on the same shared cell state, but update different pixels based on the mask. And as you can see, the blend in the cell state works very smoothly. Technically, you can use a single decoder, but generally those diverge a bit with further training, so it makes sense to blend those as well with the same mask. And that gives you the following result. And this is, again, fairly simple inputs. It's just dots and lines with a bit of a color gradient. Those are the cell states of the final result. And you can really see that the cells don't have to do a lot of work to blend from one to the other because the general values are already in the same ballpark. And just like before, you can combine this with other control maps to drive, for example, the rotation. And besides those maybe more esoteric NCA nodes and COPs, we also got two other neural nodes. Houdini 22 ships with two external models. And one of them is Meta's Segment Anything, or SAM2, that can create alpha masks based on simple user prompts. The other one is Microsoft's MOGI 2, which stands for Monocular Geometry Estimation. It's really a powerful model that bundles multiple features such as extracting depth, normal, and position information from a single image. SAM2 provides the backbone for the neural layer to mask COP. The node provides the convenient UI that lets users prompt the model underneath with simple positive or negative clicks, as well as a bounding box. It also has a few helpful built-in features to clean up the final masks. Here's another example that shows how well the model understands the geometry of an image and how you can use negative prompts to restrict the mask when the segmentation defaults to a bigger area. Sometimes the model doesn't recognize the object entirely, and no matter how many points you add, it really doesn't get better. But there is a trick. The node can output more than just the final predicted mask. Under the hood, the model predicts not just a binary mask, but values that can be interpreted as confidence values. And you can visualize those by toggling off this mask threshold. Beyond that, you can also get the image embeddings, which is essentially the model's internal representation of the image. And the third output gives you the points you prompted as geometry in world space. With those three things, you can reuse them to iteratively refine and improve the mask by running the model on a previous output. It's effectively self-improving the result based on a previous prediction, and reusing the points and the embeddings makes sure you don't have to reprompt anything, so that the slowest part, which is computing those embeddings, doesn't have to be repeated by downstream nodes. And in that case, that takes you from a very rough mask to a quite clean one without any extra manual work. The other model I mentioned before is MOGI 2 from Microsoft. It's a model that can predict this whole set of useful utility passes. And here you can see the model running on different images, demonstrating how well it generalizes across different types like CG or actual images and content scales. This doesn't have to be a pure VFX or compositing related tool. Dimitri made this example where he demonstrates how he used this depth to image from depth to drive the height and reuse this to create PBR textures based on a single flat marble image. So this can just slot in any texturing workflow you already use. The node also provides a point output and tries to estimate a reasonable camera for the scene. There's options to clean up this point cloud, and you can also automatically assign a set of specific attributes to those points, which triggers the viewport to draw them as Gaussian splats. All you need to do is click on this create a G-splat points output, which creates the points and draws them in screen space size correctly. So when you look through the camera, you see the entire image, not just the dots, but you can move through it in 3D. And that brings us to our last and final topic, which is Gaussian splatting in Houdini. And as we've just seen, and I'm sure many of you already know, G-splats are really just points with a few extra attributes that tell the viewport how to draw them. And here's what we had in Houdini 21. It's a simple utility node that takes all loaded PLY point cloud files and translates all those properties to Houdini attributes. Turning on this compute G-splats gives us orient, scale, and GS alpha, which tells the viewport how big or how transparent a given G-splat is. And toggling on this compute spherical harmonics checkbox also gives us 3 more attributes. Those are responsible for the view-dependent lighting, which makes G-splats so useful. They effectively store how the color should change based on the view angle. But in Houdini, Houdini 22, we can do much more with G-splats. You can, for example, rasterize G-splats directly inside of COPs. With the landscape example from before, it becomes trivially easy to add a bit of a camera movement to an image, for example. It just takes 3 nodes if you don't count loading the file, and you get something like this. Is this going to work for everything? Probably not, but you can get away with a surprising amount sometimes by just adding a bit of parallax to sell your shot. We'll get back to rasterizing other splats in a few moments, but before that, we should look at how to create a splat in the first place. A big addition in terms of working with G-splats is being able to train your own G-splat right from within Houdini. I will do a quick run through of what kind of tooling exists and how you can get started, but Peter Sanitra will do a much more hands-on presentation right after. I highly recommend checking this out for a real deep dive. To create a G-splats model, you need ideally 3 things: a set of images, camera data for those images, think transform, focal length, aspect ratio, and so on, and a point cloud that we can use to initialize the training. Those are commonly stored in what's known as a call map format. That's just a folder on disk that has the images and a few files to describe this extra information. This information is then passed to the training program that tries to optimize the positions, colors, orientations, opacities of those points to match the ground truth image. It's not training any neural network, but it's optimizing the point properties using classical machine learning, essentially mathematical optimization using gradient descent. It can also add or remove points to ensure the density is where it needs to be to resolve any given details in the ground truth images. When starting from actual photographs, you need to find out the camera positions from which each of those photos was taken by triangulating different matching features in the image. But since we conveniently know already basically everything about a CG scene, we can just write out the data into a call map format and generate an initial point cloud in Houdini. The core of the training pipeline consists of those 2 top nodes. The ML preprocessed G-splats top node takes a set of EXR images with camera metadata and a depth AOV. We can then grab the camera information straight from the EXR metadata and construct a point cloud from the camera position and depth AOV by turning the depth of each pixel into a point. The second node is the ML trained G-splats node. You just have to point it to the exported dataset and cook it, which should initiate the training process. Before we see that, here's a quick trick this uses under the hood. You get this camera metadata for free for any Karma render, which lets you conveniently load the cameras from any EXR file back into Houdini, for example, in COPs like this. It can be incredibly handy for all sorts of other situations where you need the camera to project on some geometry, and maybe you don't have the scene file anymore, or something else got in the way. But it's like just a very quick way to get that data back. The easiest way to get started training your own is using this LOPS recipe. All you need to do is plug in your scene in the in-stage sublayer node or load any USD file from disk. I just quickly demonstrate how the scene looks here when rendered through Karma. But once you're happy with your scene, you can head to the setup camera arrays subnetwork. It comes with a lot of convenient setups to distribute a set of cameras out of the box and has all the required passes set up. You don't have to use any of that. And for some complicated scenes, it may require you to set up custom camera arrays to get the right angles of your scene. And after setting up those cameras, all you need to do is click this cook output button, which should initiate the training process. One thing that's special about Houdini's training system is that you can train extra features into your splat. Those can be most AOVs or attributes that you rendered as custom AOVs, for example. By default, the recipe also trains on normals and albedo, which you can see here. To set this up, all you need to do is point the node to the correct AOVs before submitting and make sure that those actually exist in your lob scene. When the training has started, you can head to the ML training monitor again, like shown before with the NCA, and watch the progress of the loss. And also get intermediate test renders that show the current state of your G-splat. From left to right, you can see the ground truth image, the current G-splat result, and a heat map visualizing the loss between those two images. You can also check different views depending on the size of your dataset. And you can also view the different AOVs you're training for. So you can check the normal and albedo in this case and how that is progressing over time. Beyond that, you can also open a live training viewer, which brings you into your browser where you can easily follow every step of the training in real time. It's a full 3D viewer that lets you inspect the G-splat. There's different view options like depth, alpha, and these extra features that we set up previously. The viewer also provides high-level controls for stopping the training early or pausing it, which will trigger the G-splat being saved out to disk and exported before the final training step is reached. Sometimes this is very handy when you want to stop your topnet from cooking, but you actually want to get the output that you're seeing and not just cancel it entirely. And that's the resulting G-splat brought back into Houdini. The training can export PLY and convert to USD files, so you can just sublayer the USD file back onto your stage where it lives like any other kind of primitive. And you're not limited to only training synthetic CG-based G-splats. The node also has a basic photo-based training functionality. Just set the dataset type to SFM call map, and you can train on any conventional photo-based dataset. You have to create that call map dataset first, though. There's currently no way to do this in Houdini, but there are good external options available to do that. Epic's reality scan, for example, is free and lets you estimate and export your cameras and images to a call map structure. From there, the process is practically the same. You can watch the training, which I sped up quite a lot here, and it's really satisfying seeing the scene clear up and all the details getting sharper over time. You can move around in the scene and inspect any areas of interest. Eventually, you can bring a PLY file into subs to do with it wherever you want. And as it's essentially just points. A final neat thing enabled by training on albedo and normal AOVs is COPS-based relighting. You can bring in your G-splat and extract different attributes you trained on. You can then rasterize it using any camera and apply any AOV-based relighting techniques you usually already use when working with CG renders. Here I'm adding a pink key light and a bit of a specular Phong reflection, and this works as expected on the entire frame range. Yeah, and I think that's it from me. I hope you have a lot of fun with Houdini 22 and some of the new ML features. Thank you very much. Any questions? Do we have time? Yes.
We have time for one question. I saw you first.
Hiya, thank you for the talk. It was really interesting. I want to know how well, if at all, is Houdini currently with training 4D Gaussian splats, like animated Gaussians, or is it just statics at the moment?
Great question. The training system is designed to train single 3D Gaussian splats. We had this example in the keynote about an explosion sequence being trained as a Gaussian splat. You need to do some trickery to really get this to work nicely. Depending on how long you have to render your actual data and how long you have to train, you can actually achieve perfect results because training long enough would give you clean enough Gaussian splats that actually don't flicker. But if you're limited to a few cameras per frame and a limited point cloud to keep it relatively lightweight, you have to come up with other techniques The training system allows you to basically load a previous G-splat as a checkpoint and start from that. And what we did for the explosion demo is that you can basically train one frame, get this frame into Houdini as a G-splat, advect it with the velocity field, take it back to the training, train next frame, and so on. And that lets you achieve quite a lot if you're willing to put in the time. But yeah, it's definitely something for the future.
Okay, thank you.
And I actually think we've got time for maybe one or two more. I think I saw somebody over here as well. Yeah.
Hello, I've got a lovely open-ended one. Great talk. I like breaking this stuff. This is all very well, and like I saw a few areas where maybe you can manipulate it in the training stage and in the reconstruction phase, but you know better. What's a good way to break it? Like for experimental looks, for example, not for like real production. I don't know. Feels like an open-ended thing.
You can, this goes like in the same direction, like starting from something that you bring in from within Houdini, and you can override a lot of the settings and disable certain optimizations. So for example, you can lock points in place, you can turn off like it's called densification, which adds more points to different areas, but you can basically force it to keep the same point count. And I think you can achieve some very interesting stylized results by locking some of that stuff or starting from something that you prepared in Houdini in some way. Yeah, but there haven't been that many tests in that direction yet, so I'm like curious to see if
I'll
anyone
go break
dares. Yeah.
Thank you.
Have you experimented with G-splats and Houdini into Arnold?
The first thing I did was to... Spoilers, yes. But the first thing I did with the Karma splats was just add noise, and it turns it painterly. So I was like, I need to do more stuff to see how much more I can break it. But for Arnold, it's going to work the same as Karma, right? Where it's the same data going in. So, but yeah.
One more up here, yeah. Do the shuffling. Do you want me to?
Thank you. Great presentation. You talk when talking about training G-splats is that it's very easy to get AOVs out of them, and that's generally a cool strength of ML learning and stuff. It doesn't really tend to care about how many layers you've got going in. I'm curious with the Neural Cellular Automata. I could see you could change the signature of it. I'm wondering how many layers you could actually feed into it, because it feels like a prime example to just feed a full PBR texture into it with diffuse and roughness and normals and metalness and all that.
Thank you, first of all. Currently, you can't change the signature, but technically nothing is preventing the system under the hood from producing more channels as an output. This was more of a side project, to be frank, so there's definitely room to add the support that you're talking about for PBR textures. And the second paper I linked to, they're already kind of doing this. So they're training on multiple textures, but you need to be kind of smart to formalize this in the training to not diverge in the channels, because otherwise they drift and then you get a height map that doesn't match your RGB. So you need to do special things that currently this doesn't do, but it could in the future.
That'd be really cool. Thank you.
Thank you.
Great stuff, Jakob. Thanks for taking us through that.
Thank you.